Welcome to Google Cloud AI Developer Relations Virtual Training for Junior Data Scientists. In this episode, we'll cover Hyperparameter Tuning. My name is Andrew Froelich, and I'm a staff member at Google Cloud AI Developer Relations. So in this session, these are the things we'll cover. First, we'll talk about weight initialization and its importance of numerical stability for a model. Then we'll talk about Warmup, which is a supervised version of pre-training for numerical stability. And then we'll start getting into the hyperparameter search itself. And we'll start off with some of the do-it-yourself manual approaches. And then we'll look at automatic hyperparameter tuning using Keras Tuner. And then we'll go look into the learning rate schedulers, and we'll look at both built-in and do-it-yourself approaches. And then finally, we'll wrap up with conventional approaches to regularization. So weight initialization. Well, when you first start training a model from scratch, all the weights need to have some initial value. And this process is called initialization. Well, for simplicity, one could say, well, why don't we just set all the weights to the same value? Let's say 0. Well, this is a problem because of the way gradient descent works in backward propagation, that if all the weights started off the same, then each weight would have the identical update. And thus, in this case, you would have a neural network that is symmetrical and is equivalent to just one node. So our initialized weights cannot be the same. So we need to set the weights in the model to some random distribution of values. And ideally, this distribution should be small, like less than -1 and 1, and be centered around 0. And here I'll cover some common distributions that have been used. So a long time ago, we used a uniform distribution, and that's not used anymore. Later, the favorite was the Xavier, or known as a Glorit distribution, and this was really popular when models used the hyperbolic tangent as the activation function. This was before the ReLU. And this random distribution is a normal distribution centered at 0 with the standard deviation set to this formula here, where fan-in is the number of inputs to that specific layer. Later, after moving to a ReLU, it was found that this distribution of changing from a 1 to a 2 gave better results, and this distribution is known as he-normal, and that is what's used today. So to specify the he-normal distribution, you're going to specify on every layer that has parameters to learn. So that'd be like a dense layer and the convolutional layer. And you're going to specify it with the keyword kernel initializer. So here we have a convolutional 2D. You're familiar with these parameters, the number of filters, the kernel size or filter size, the strides, the padding, the activation here is a ReLU, and now I've added in kernel initializer equal he-normal. Same thing with dense. It's important to actually add this because in Keras, the default is a Glorit, which is really not appropriate anymore for a ReLU. Okay, so beyond just initializing your weights from some random distribution, even a good or ideal random distribution, no two draws from that random distribution are equal. That is, in other words, some draws from that random distribution for weight initialization will produce better results than others. And so the lottery hypothesis, which was very popular in 2019, proposed that large models, these models with overcapacity, had high accuracy because they are really a collection of small models. And each small model had a different draw from the random distribution, and where one of those draws is what they called the winning ticket. Now, many people, including myself, pursued this direction, and subsequent attempts to try to identify and extract the submodel with the winning ticket into what was called a compact model from the trained large model never panned out. The derivations of the lottery hypothesis principle are still used. Typically, when you're in production, you see people doing sort of this pre-training for weight initialization, they're going to do it this way. They're going to start with a random distribution, like a mean normal, and they're going to have a reference model, okay? And they're going to take a large number of instances of that model, 10, 100, 1,000. Each instance will have a separate draw from that random distribution, and then they're going to run it for a small amount of epochs on a smaller number of steps. And for every one of them, they're going to look at the results, and based on some objective function, like the validation loss, they're going to sort of guesstimate which one of those draws is the winning ticket. And they're going to start with that weight initialization when they go into training. So here's code, example how you might write your own lottery hypothesis. So you have something here that's going to create your reference model. And I just have this based on a ResNet 50 where I'm going to add in my own classifier. And every time this is instantiated, that's going to have a different draw from the random distribution. So my lottery, I kept it simple here, is just going to be 10 of them. I'm going to make 10 of these models. Each one has a different draw from the random distribution. I'm going to use the CFAR10 as an example here, data set. Got my image data generator to use as a feeder. And what I'm going to do over on the right side here is I'm going to spin through this list of models, each with a different random distribution. And I'm going to do a little bit of pre-training, a small number of epochs and a small number of steps per epoch. And at each point, I'm going to record the objective function. In this case, I'm looking at the validation loss. And if that loss is better than the previous one, then I'm going to just set best equal to the current model based on that loss. Okay. Well, that's one approach to numerical stability. Another approach is called Warmup, and this is different from the lottery hypothesis. In this world, a large model is viewed as being divided into your higher levels, your higher layers, and your lower layers. And the presumption is the lower layers provide numerical stability to the top higher layers during training. That is, the lower layers provide the numerical stability for the higher layers to learn the winning ticket, the initialization draw. So if numerically stabilized, then the bottom layers in the model, which is also the higher layers, are the winning ticket. Okay, so how do we do warm-up pre-training? Well, we start with using a very tiny learning rate to avoid causing large swings in weights and get the weights to shift towards that winning ticket. And typically the values range in this range. So we start with one reference copy and one draw from the random distribution. And each time we do a training run on it, a warm-up training run on it, we're going to slightly increase the learning rate. And we're going to keep repeating that until we work our way all the way up to the initial learning rate. And slowly, those weights shift and shift and shift towards numerical stability and what we would call the winning ticket. And this is really the main conventional way we are pre-training or warming up models now. So this code just shows how you could write your own warm-up. So we need an initial warm-up learning rate. You can see I made it pretty small. What will be the final initial learning rate? How many epochs we're going to do? In this example, I kept it small, 4. Then the step would be, just the initial the difference between the initial learning rate and the warm-up learning rate. So that's the distance we're going to cover divided by the number of epochs. That's how much we're going to increase in each step. We have something that's going to make our model here, and we're going to compile it with the warm-up learning rate. Okay, then we're going to do our own learning rate scheduler, which we'll discuss in more detail later. But in this case, on the very first epoch, it will start with the initial warm-up learning rate, and every one after that, it'll just progressively increase that learning rate until it gets to the initial learning rate. So here, I'm going to import from Keras callbacks the learning rate scheduler, and I'm going to instantiate an instance of the learning rate scheduler. And when you do that, you want to specify the function that is the learning rate scheduler we wrote this warm-up scheduler. That's why that's here. And then when we do our training on the callbacks parameter, we're going to add to our callbacks list the learning rate scheduler. And if you're not familiar, well, I've discussed this before, if you're not familiar with it, at the beginning of every epoch, your warm-up, your learning rate scheduler will be called, and in there you implement how you want to change the learning rate. Okay, pause for a moment for water. Okay, so now we got numerical stability for our weight initialization, whether it's by lottery or by warm-up. And so we're ready to do hyperparameter search, which is also known as hyperparameter tuning or hyperparameter optimization. Now, one thing I'm going to point out here is you do this after numerical stability. It doesn't make any sense to try to do your hyperparameter search before with an unstable model. Okay, so the goal of hyperparameter search is to find the optimal hyperparameter setting or near optimal that will maximize the training of your model for your objective, like the evaluation accuracy. Typically, when training a pre-configured model, the only hyperparameters we attempt to tune are the learning rate, the batch size, the learning rate scheduler, as I mentioned in that previous slide, and then finally regularization, which we'll discuss at the end. Okay, so I like to visualize the search space with this type of picture here. And what it's trying to reflect here is these are all the different combinations. And here I'm just visualizing as a three-dimensional space, as if there were only three hyperparameters to tune. In this case, batch size. Oops. Yeah. Okay, I'm sorry for that. Yeah, unbelievable. Threw me off. Okay, so this is our search space. And in this volume of our search space, most of these combinations don't produce any good result. Not an optimal result, not even a near optimal result. But here and here and there are these little green areas that do produce what we could say the optimal results. Okay, but they're very small and very hard, very infrequent and hard to find. Okay, but around them is in the vicinity, these yellow areas are these larger areas that we sort of produce near optimal results. Okay, and those are going to be a lot easier to find. Okay, so oh, that really threw me off. Okay, so let me start with a manual method. I have a lot of experience training computer vision models and have a strong intuition when it comes to selecting hyperparameters. And I'm able to use this learned intuition to do a manually guided search. So I'm going to kind of show you how, if I were to do it manually, my general approach. So I would start off by coarse tuning the initial learning rate. And then I'm going to tune the batch rate, and I'm going to come back and fine tune the initial learning rate, and then I'm going to tune the learning rate scheduler. So let's go ahead and show you how I do it. So when I start, I'm going to start with a constant batch size. And typically, if I'm working with a small data set, I just set it to 32, or a large one to 256. Those tend to be the low ends. Okay. Then I'm going to pick a range of typically 3 learning rates, each a magnitude lesser than the last. So if we look at this, I might have 0.01, then 001, then 0001. Okay. And I'm going to run an initial training with a few epochs on each of these learning rates and pick the one that has the best validation loss. And then once I got that, I'm going to sort of do this divide and conquer thing. I'm going to pick halfway points between the best and the previous or the next. And I'm going to do another run and see if that halfway point is better. So if this one was the best, I might go halfway between here, which would be 0.005, see how I did. I might try the same thing on the other end. And if either one is better, I just repeat that, divide and conquer again. Again, halfway between the new point and the next, and I'm just kind of fine-tuning or honing in to that, that spot. And generally, I find this gives me a high likelihood that I'm in a near optimal area, that I get into this yellow space here. Okay. Then I'm going to tune the batch size. So I'm going to progressively increase the batch size by a power of 2. So if I start at 32, I'm going to try 64, then 128, so forth. And I'm going to run a few epochs and see if it improves. Now, if it doesn't improve, then I'm just going to stop and select the previous best batch size. And at this point, there's a high likelihood that I've gotten closer to an optimal green area. I'm in the yellow area, and I'm getting closer to that green area. Okay. So now I'm going to go back and retune that learning rate, because that learning rate was initially based on an arbitrary batch size. Okay. And when you work with larger batch sizes, you have less variance in the batch. Okay. And with less variance, we can typically raise the learning rate if we have increased the batch size. So if we didn't if increasing the batch size did not give us a better result, we'd stop. But if it did, I would then fine tune. So I'm going to repeat the same tuning experiments for the learning rate when I did the coarse one, but I'm going to make a new range. So I'm going to take the value that was the one picked for the coarse, and I'm just going to go ahead and make it the center point of 3, and then have one be a magnitude greater and the other one a magnitude less, and I'm going to repeat that whole tuning again. Okay, so after that, then I want to tune the learning rate scheduler. And I'll start by doing a full training with early stop when the validation accuracy stops improving. And I generally try using the Cosine Annealing version of the learning rate, which we'll discuss subsequently. And if that makes a significant improvement, I generally just stop there and say good enough. Otherwise, I'm going to look back at the initial full run, and I'm going to look at every epoch, and I'm going to try to find in that output where the validation accuracy plateaued or diverged. So remember, these models are built with overcapacity. And if we train past a certain point, we're going to have memorization occur in that overcapacity. And we're going to spot that by the validation loss plateauing and even eventually diverging. And what I want to do is create a learning rate scheduler that's going to drop the learning rate by a magnitude at least one epoch before it hits that point. Okay. And this generally gives me a really good starting point, and I can now focus on other pre-training steps like augmentation and label smoothing, which we'll discuss subsequently. Okay. So that's my version. Okay. But there are some standard techniques for doing automatic tuning or hyperparameter search. One of them is called grid search. This is sort of the historical or the grandfather one. Okay. And it just says you take all your hyperparameters and all the possible values, and you just do a grid. You actually take every combination, and you're going to try every combination like a grid. Okay. Well, this is really only practical with a few parameters and values. Here's some code I wrote if you wanted to do your own hand-rolled grid search. I'm doing here what the learning rate has just 2 values, and the batch size has just 2 values. So these 2 for loops will make every possible combination of the 2. For every one of those combinations, I'm going to get a copy of the model. I'm going to set the learning rate. I'm going to do some training, setting my batch size. So there's my combination. I'm going to look at the validation accuracy here. And if it's better than what it was before, that's the one I'm going to save. So that's a grid search. And I mentioned that's not practical if there's a large number of variables and a large number of parameters. So the next thing people did was random search. And you might ask yourself, how could a random search be computationally less expensive than a grid search is just random? Well, this really goes back to that picture I showed you of the hyperparameter space. And what we know is only a small portion of that hyperparameter space has an optimal combination. And thus, we have a very low probability of finding one randomly. But we do know that most of those really good combinations, that green area has this larger yellow area that's near optimal. And actually, we have a very substantially higher probability of landing in one of those using random search. And once we find a near optimal combination, we know there's a good likelihood that there's an optimal combination in the vicinity. So let's go back to that picture here. Okay, so this is the area we were talking about where randomly we're going to fall in a lot and not find things, but once in a while we're going to fall into one of these yellow spaces. So let me just kind of go over the basic algorithm. So you're going to set some parameters for the boundaries of your search space. So this box here is our boundaries. This is the volume of combinations we're going to randomly select from. We're going to do a random search within the search space. And once we're in a near optimal combination, then we're going to actually narrow our search space to the vicinity of that. So now it's just this instead of this whole volume. And then we do random selections within that. And so really only two things can happen. Within a number of trials, we usually limit the number of trials. If we find an optimal search space, we stop. Great. If not, because maybe this area that we picked is still outside and doesn't overlap with the optimal, or maybe we just never picked a value in there, we'll just back out and keep repeating the random search on the outer space until we find another one of these that we jumped into, and then reduce the search space to that vicinity. Okay, so that's how you might do your hyperparameter tuning on your own. But a lot of people prefer nowadays to use an automatic version that does the work for them. So I'll show you the Keras Tuner. It's an add-on module to TF Keras, and it does automatic hyperparameter tuning. It has two methods, the random search and the hyperband search. And I'm going to show you how to use it for the random search. Now, I'm going to also point out that all these advanced search methods, random, Bayesian, hyperband, Vizier, all of them are working on the same principle. They're doing some kind of beam searching in that space, that volume, and they're looking for those near optimal areas. And then they're reducing their search to the vicinity of that, and they're applying some other search algorithm that's optimized for that location, trying to hone in on an optimal set of combinations. Now, like all automatic tools, Keras Tuner has pros and cons. Being automated and fairly straightforward is obviously a good thing. But for me, the lack of the ability to tune the batch size is a big con, which you have to tune manually. So the Keras Tuner does not come by default with TF Keras. You have to separately install it. So it's just the pip install for installing it. Okay, so when I want to do a random search, I'm going to go from Keras Tuners. I'm going to import the random search method, and then I'm going to instantiate it, and it takes 3 arguments. One of these is what they call the hyperparameter tunable model, which I'll discuss in a moment. Then what the objective function is, you're going to base your decision whether this combination is a better combination or not. In this case, I just set it to the validation accuracy, but you could set it to anything. And then the maximum number of trials. I just kept the numbers low for the purpose of demonstrations here. Okay, so what's this hyperparameter, what we call the hyperparameter tunable model, or typically denoted as HP_model? Well, it's a function that's going to create a model. And it's going to take a parameter, HP, that comes from the tuner. The tuner sends in this hyperparameter control. Okay, so what you want to do in this example, I'm just going to go ahead and I'm going to load a pre-built model that's been numerically stabilized, and I want to tune it, let's say, just for the learning rate. So in this case, the learning rate is set in the compile function. And if you notice here, when I get to the optimizer and I go add them, instead of putting a fixed number in here, I'm using hp.choice. So this HP has several methods on it that allow you to specify choices or a range of values. And that's where the random part is going to come from, where it's going to randomly pick combinations. In this case, I kept it simple. There's really only one variable here. And I'm saying the random choices to pick from are these 4 values. And it's going to randomly pick one, configure it, and return that model. Okay, now that I've written my HP method or HP model method, it's time to do the trials and get the result. And to do the trials, we're going to invoke the tuner search method, and its parameters are the same as the fit method. So here we have tuner.search, and I got my training data, my labels. Here's where I mean you can't tune the batch size, you have to hard wire it. Okay, and then the validation data, because in my case, I wanted to base the result on the validation data. I run that, it does its number of trials, and when it's done, I want to get the results. And so you can use the method get best models to get back the corresponding best models. You can also specify how many you want. So the first best, the second, the third, the fourth. In this case, I'm saying 2. And that's going to return a list. And the best model will be the first element in the list. Another thing, when you're doing this, it saves the results in the folder, and by default, that folder is named untitled project, or you can specify a particular name with this parameter, project name. And it's important to clean it up, because if you do another run on a different set of parameters or a different set of models and you're using the same folder, it is going to trash the results. Okay, so let's now move to the learning rate scheduler. So we could get really good results with a constant learning rate, but it's not as effective as adjusting the learning rate during training. And typically we want to progress from a larger learning rate to a lower learning rate during training. And we're going to start with a large learning rate that's not too large to cause numerical instability. And typically that learning rate we're going to find by hyperparameter tuning. And you want the learning rate to explore more paths for local optimals to converge on. That is, increase the likelihood of finding the best or at least a good optima. And we want to make some initial large gains towards convergence. That is to speed up training. So that's the benefits of starting with a large learning rate. But once we are making good progress down a good local optima, if we keep using that high learning rate, we may start oscillating back and forth without converging, or even inadvertently jumping out of a good local optima and start converging in a less good optima. So as we get closer to the convergence, we want to start lowering the learning rate to make it smaller and smaller and smaller, as to not oscillate and to maintain finding the best path in the local optima to converge on. Okay, well, there's several ways of doing it. One way is built in. So in TensorFlow Keras, Decay is all the optimizers support the decay option parameter here. And that decay here is a time decay, is implemented by this formula. I won't go into details other than to say after every epoch, your learning rate is progressively gets smaller and smaller and smaller and smaller. So here in the compile method, when I'm setting the optimizer here, for example, I'm using the app atom optimizer, and I'm setting the learning rate to 0.1. I'm specifying a non-zero decay. So my learning rate won't stay constant, it will constantly decay. And this is typically the range people use for decay in Keras. Okay, so this table just kind of shows you what the learning rate would change if we use those same parameters. Start with 0.1 and decay of 1 to a power of 3. Okay, 10 to the 3, excuse me. So on the first one, we're going to have here, basically 0.1. It's kind of how it's represented there. And when we go to the next one, as we decrease by 0.002. Okay, we go to the next one, it decreases a little bit more, 3. Then the next one is going to decrease by 4, then 5, then 6, then 7, 8. Notice the progression. So as the time decays, that decrease gets bigger, 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 bigger. It just starts off really small. Okay, so let's put together a learning rate scheduler. Okay, so from TensorFlow Keras callbacks, we want to import the learning rate scheduler. Okay, object. So we're going to create a learning rate scheduler. And as I pointed out before, it's a function that takes 2 parameters. The first one is the epoch. The second one is the learning rate. That's what's going to be passed into it by the training method. It's always invoked at the beginning of the epoch. So the very first epoch, which is epoch 0, we want to return that first learning rate. And then we're going to implement, here I have this comment, your learning rate scheduler that's going to give you a new value, and it's the new value you want to return. So here I've compiled the model. I'm going to create my callback. Okay. And then when I do a fit, I'm going to use the callbacks parameter and specify in its list my learning rate scheduler callback. So at the end of, or the beginning of every epoch, this function will be called. Okay, so I'll cover a handful of methods for a learning rate scheduler. The basic one would be the ramp method. And this is a fairly common strategy. I've mentioned it already. So during an initial trial full training after tuning, you're looking at the validation loss and accuracy, and you're after every epoch, and you're looking for that point where it's going to plateau or diverge. And what you want to do is just before that, back up a little bit. And let's say it occurs at epoch 38, maybe at epoch 35, you suddenly want to dramatically drop the learning rate, typically by a magnitude. That's your ramp. So in this hypothetical one, I did a full training initially. I saw that this negative or plateauing occurred around epoch 38, so I decided to set the ramp at 35, and my learning rate scheduler is pretty simple. Stays at the initial learning rate until it hits the ramp, and then it reduces it by 1 magnitude, and from then on, the remainder is the same. So that's what this picture depicts. I hit epoch 35 here, I do that big drop, and then the rest of the training is at 1 magnitude less. Okay, another method is called the constant step method. And in this method, we want to go from the initial learning rate to 0 on the last epoch in even increments. And this is pretty straightforward. You take the learning rate and you just divide it by the number of epochs, and that's your step value or the increment you're going to decrease it by. So here's a little bit of code that shows that. Let's say I had 200 epochs. That's my learning rate. So my step is going to be the learning rate divided by the epochs. Then after every epoch, my learning rate scheduler is called, and it just simply decreases the learning rate by the step. And on the very, very last epoch, the learning rate will be 0. Okay, cosine annealing. Now, this method has been very popular among researchers and appears frequently in research papers. It's also known as the cyclic learning rate. And the concept here is to progressively lower the learning rate, is to do it in cycles. So you start lowering, 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 but before you get too far down, you actually go back up, but not as far up as last time, and then you go lower, 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 and a little bit lower this time, and then you stop, and you go back up, but not as far as last time, and then you go lower, 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 just a little bit you did last time, and you keep repeating this. That's the cyclic learning rate, okay? Now, there are some advantages, and that it allows you to explore other local optima at times, jumping out. It's like doing a beam search, and it's good at escaping saddle points. And so here, I'm going to use these three picks to sort of help you understand why this works. Okay. Now, if our function was a linear relationship, okay, then it would just be a straight line. That's why we mean by linear. So any learning rate is just going to drive straight down to the global optimum. Okay. This convex is usually a picture that in the past, a lot of times was represented to show the loss space and how the learning rate was affected. But the problem is the loss space really in a model is not convex like this. That implies there's a polynomial relationship. But if it was, and it was a constant learning rate and it was a high one, you might go dive down fast, but hit a point here where you start oscillating back and forth. That's why you want to lower, 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 so you can get to here without bouncing back and forth. But come on, the reality, our models are solving non-linear relationships. So the loss space, you have to think about it as being valleys and hills and plateaus. And so this rough drawing here just shows like here's a local optima, but then it goes back up. Here's a plateau known as a saddle point, yet here's a different one for a global optima. And what we want to do is have a learning rate scheduler that if it's diving down here, gets us out of that. If we're stuck here, we can escape it, and we kind of are beaming around until we find this one and we can converge down on it. Okay. If you wanted to write your own cosine annealing, here's the function for you. I won't go into too much detail, okay? But you're going to pass in the epoch and the learning rate, and this other thing called alpha. And that's like a bounding function. If you want to bound the minimum learning rate, you won't go below this value. This is the formula. Again, I'm not going to go into detail, but gives that cyclic nature. And then in your learning rate schedule, you just return the cosine decay of that. But in TF2.x, they built in cosine annealing, so why write it yourself? Might as well use the built-in version. So you're going to, from TF Keras experimental, you're going to import cosine decay. You're going to instantiate your learning rate scheduler using the cosine decay, giving it the initial learning rate, your decay steps, and your alpha, if any. And then when you're training it, you just add it in. Okay, so we're going to wrap up with regularization. That is sort of the modern way of doing regularization in your model to prevent overfitting. And the most widely used form today is what we call weight regularization, or also known as weight decay. And weight regularization is applied on a per layer basis. And it's going to add some noise to the update of the weights during backward propagation. And this noise is relative to the size of the weights, or you can refer to the noise as a penalty. And layers with larger weights are going to get a larger penalty, and layers with smaller weights will get a smaller penalty. And so this sort of squashes them towards each other. And in doing so, that adds this regularization effect on a per layer basis. Okay. What is the right value or method for regularization has really been kind of worked out in these state-of-the-art research papers, and they're typically ended up using L2 weight regularization. And they typically, if you look at the papers, did it in ranges from this is 0005 to 001. Now, from my own experience, whenever I use values above 001, it tends to be too aggressive in weight regularization, and the training doesn't converge. And the way you add weight regularization is a keyword parameter, kernel regularizer, and you add it onto any layer that has learned parameters. So for example, conv2d and the dense layer. Here's an example of doing it. So from TensorFlow Keras regularizers, I'm going to import the L2 method. And here's a conv2d. So I have one additional parameter. Here's my filters. Here's my filter size, my strides. And here I'm adding the kernel regularizer as an L2 with the value 0.001. Okay, so the final way, or not final, but final part of this for regularization is label smoothing. And label smoothing takes regularization from looks at it from a different direction. And what we find is that when we penalize these weights updates to prevent memorization, these models tend to be overconfident in their prediction. That is, they have a high probability value. For example, if it might predict an apple of 97% probability, but an orange only 3%. So there's this huge separation. Okay, and we refer to those as hard targets. And so a hard target is like when you're in one hot encoded ground truth, whatever is true, the apple is a 1 and everything else is a 0. Now, the pro on that is we get a really clear delineation in most cases between the predicted label and the other labels. The apple is 97 and the orange and the pear, and that are these tiny little numbers. But the negative is we're very overconfident, and that overconfidence is prone to overfitting. And the distances from the truth label, example of the apple, and the non-truth labels can vary greatly. That is, the distance between apple and orange may be totally different between the distance of apple and pear. So label smoothing aids in generalizing the model by making the predictions a little less confident, which results in the distances between the ground truths and the non-ground truths to actually cluster together. That is, to be almost equal distance from the truth that's being predicted. And the way we do that is we're going to alter our one-hot encoded labels from being an absolute certainty, 1 and 0, to something a little less than absolute certainty. We're going to donate that as the alpha. And so typically we try something like an alpha 0.1, which means that we're going to set our labels to a 90% confidence. That is 0.9 instead of 1. But on the other end, all the non-truth ones, the 0, we're going to add the same amount to them. So they're going to be 0.1 in this example. And 10% or 0.1 is actually one of the most common values people use for label smoothing. So let's kind of look at how it works. So in this case, because these values aren't absolute, 1 and 0, we call them now soft targets. So your soft target, your truth value is 1 minus the alpha. Your false value is 0 plus the alpha. And there's a really easy way to implement this. It's built in TensorFlow, TF2.x in the losses. Okay, they now have a parameter called label smoothing. So here I'm going to import the categorical cross entropy loss function. And when I compile it, I'm going to instantiate it, and I'm going to add in the label smoothing parameter and set it to 0.1, and I'll automatically get label smoothing during training. Okay, so I want to thank you for watching. Another one of our training sessions from Google Cloud AI Developer Relations.